Section 12.2, question 26. Find the volume of a given solid bounded by the plane z equals x, y equals x, x plus y equals 2, and z equals 0. Before we do anything, we should get a visual of what the solid looks like. And we could try to sketch it by hand. But as one of you pointed out in class, Desmos has a really nifty 3D graphing calculator. So we're going to go take a look at it. I just searched Desmos 3D graphing, and this is where it took me. All right, so let's try typing in the equation. Z equals x. How nifty, we got this plane. See, we got plane. Okay. We have y equals x. Extend to 3D. Well, that's interesting because now because it only has x and y, it knows that we can interpret it as a xy two-dimensional thing. And if I click this little button here, it will take me to the xy orientation. And now we just see what it looks like, the projection in the xy plane. But also notice that if I go back to 3D and turn back on the first plane, y equals x is not currently graphing as planes, graphing as a line. Apparently, in this Desmos 3D graphing calculator, when you put in an equation in x and y, it assumes it's limited to the xy plane, but you can extend it to 3D by simply translating it parallel to the z-axis like this. Now we can rotate it and see all that. I believe the next plane was x plus y equals 2. And being an equation of just x and y, I assumed it was going to put it in just the xy plane, but we can extend it to 3D by translating it in the direction of the z-axis. Let's turn the other planes back on. And of course, z equals 0 is the ground. Why am I not seeing you? Because you're in gray. Gray is boring. Let's do red. Okay, so the thing we're looking for is bounded by these 4 planes. So it's above the floor and trapped by all of these. I think I can see where it is. Let me zoom in a little bit. There we go. Let's take a top-down view for a second. See the purple and the green planes, this one and this one? It's over here below the blue plane, but above the floor. So it's kind of hiding in this corner right behind this green wall. And if we rotate it this way, it'd be behind this purple wall. And rotate it this way, it's behind that blue wall. So I can kind of see where it is. Now, can I sketch this manually? Probably not do a very good job of it. But let's see if I can do this. First off, let's not do it in yellow. Okay, so in the xy plane, y equals x is this perfect diagonal line. X plus y equals 2 has both x and y intercepts of 2. So let's just mark off 2 on the x and the y axis. Connect them. And we're bounded by the plane z equals x. Now, the plane z equals x contains the x-axis. Because when x equals 0, z would equal 0. So it would contain the x-axis. No, wait. Z equals x. That means y doesn't matter. Okay, in the xz plane, we would have this diagonal line here, but then it would get translated in the y direction. So that would be like the ceiling of it. And then we would shoot this up to there, and it would cut down something like that. So we have this sort of tetrahedron. I see it. I don't know if you can see it based on what I've drawn. Let me try to get rid of something here. So it looks something a little bit like that. So I know what I'm going for, but the important thing is what's the projection in the xy plane? Well, let's, what am I sharing right now? Make sure you guys can see what I see. Let's switch this to the xy orientation. And for some reason, when I do that, the y equals x plane disappears. If I tilt it a little bit, you'll see it. So let's take this back down to here. There we go. So we put those 2 planes back into the xy plane, and we have those lines. So it's pretty easy to see what the projection looks like in the xy plane. So let's draw that here. X, y. This top equation is x plus y is equal to 2. The bottom one is y equals x. And of course, the left side would be x is equal to 0. So this is the region over which we're integrating. And we simply have to integrate the top plane, which is equals x, over this region. All right, so we'll call the region D. Okay, so we need to evaluate the double integral over the region D of x dA. And again, it's x because z equals x. This is serving as the top of the solid. So we're integrating to find the volume underneath that thing. And again, all this over here determines what d equals. Actually, that's not entirely true. This determines what d equals in the xy plane. What z equals 0 is the bottom. So basically, we're integrating top minus bottom over that region, D. All right, so let's think about how we want to integrate this. Do we do dx first or do we do dy first? Well, if we do dx first, we have to go x equals on the left to x equals on the right. Although the left side of this is one curve, the right side is not. So doing the dx first would be a bad idea because x equals is two different curves on the right. But if we took the bottom to top view, the bottom of this lamina is this, the top of it is that, and both of those are single curves. So we would go y equals x on the bottom and y equals 2 minus x on the top. So we would want to do the dy integral first. All right. So let's make this the way I want it to look. Desmos just updated their toolbar and I'm still getting used to it. Okay, so again, this lamina, the bottom, from bottom to top, the bottom is one curve, the top is one curve. So we should integrate from bottom to top, which means we do the dy integral first. All right, so we will do the dy integral first. And on the bottom of this lamina, y is equal to x. And on the top of the lamina, y is equal to 2 minus x or negative x plus 2, whatever floats your boat. And then after that, we would do the dx integral from left to right. And on the left, x is equal to 0, but what is x equal on the right? In other words, we need to know what x equals right here. So basically, we need to know that ordered pair. Well, if we solve the system, x plus y is equal to 2, and y is equal to x, without dilly-dallying, you'll get x and y are both equal to 1. They're equal and their sum is 2, which means when we do the dx integral, it's going from x equals 0 on the left to x equals 1 on the right. And now it's an easier problem to do. Starting with the integral from x to 2 minus x of x dy relative to yx is a constant, so its antiderivative is xy. This is going from y equals x to y equals 2 minus x. We substitute 2 minus x for y, we get x times 2 minus x. Minus, if we substitute x for y, we get x times x, which is x squared. So we end up getting 2x minus x squared, which is 2x minus 2x squared. Then our outer integral is simply from 0 to 1 of 2x minus 2x squared dx, which is going to be x squared minus 2/3 x cubed, evaluated from 0 to 1. When we evaluate it at 1, we'll get 1 minus 2/3, which is 1/3. And when we evaluate it at 0, we get 0. So it looks like the volume of our solid is 1/3.